We're going to do day one of review today. We're going to start off with some mechanics. We have a baseball traveling 38 meters at a velocity of 35 meters per second. How much time does it take to travel the 38 meters? Now what I'd like you to do is, using your reference table and calculator, write down all your knowns and unknowns and plug them in. I'll give you a moment, but I'd like you to pause the video in order to do your work. Alright, so here we go. I have my knowns and my unknowns. I have d equals 38 meters. My average velocity is 35 meters per second. I'm looking for time, so I'm going to use my equation, v bar equals d over t. Solve for t, and then I'm going to substitute my 38 meters in, my 35 meters per second, and I get t equals 1.09 seconds. Alright, try your next one. A car traveling at 45 meters per second brakes at 4 meters per second squared. How far will the car travel to a stop? Alright, write down your knowns and unknowns. VI is 45 meters per second. A is 4 meters per second squared. Might be something we need to change. VF is 0 because it's going to a stop, and we're looking for D. So find me the equation. We end up with VF squared equals VI squared plus 2AD. Now the trick in this one, you know how I like to put tricks in, is it's braking. So 0 meters per second squared equals 45 meters per second squared plus 2 times negative 4 meters per second squared D. It had to be negative because we're decelerating. Solve, and we get D is equal to 253 meters. All right, try our next one. The next one's a free fall problem. So again, write down what you know and what you're looking for, and then pick the equation. We're dropping a small car from a building. How long does it take for the car to hit the ground? What's the velocity just before it hits the ground? Remember, the car does not have a final velocity of 0. It's going to hit the ground going pretty fast. My knowns, I've got 0 meters per second because its VI is 0. And we have our acceleration is 9.81 meters per second squared. My distance is 28 meters. I'm looking for time, and I'm looking for final velocity. So for my first equation, I'm going to use D equals VIT plus 1AT squared. Substituting everything in, I'm looking for D. And I get T to be 2.4 seconds. Now for the other one, I can use my time and solve for VF equals VI plus 8T. And I get 23.5 meters per second for VF. I could also use VF squared equals VI squared plus 2AD. Alright, now we're going to review vectors. We're going to turn our vectors, see how this, we have a start, and then it goes tip to tail, tip to tail. We're going to turn it into a parallelogram, so I'm just going to redraw my 13 down here. And I'm going to redraw my 8. And now I am just going to draw my resultant from start to finish. Right down the middle. Remember, the arrowhead is right here. A little bit darker. There. My arrowhead. To solve, we can do a squared plus b squared equals c squared. And to get the angle, we're going to do opposite over adjacent. So if we are looking for this angle here, we would do the opposite side, 13 divided by 8, and we would take the inverse take. So I solved the tan of theta, 53 degrees, and I solved the hypotenuse using a squared plus b squared equals c squared over 15.3 meters. I will remind you with solving for tangent or any of the trig functions, make sure you are in degree mode. So if we try one that's a little bit harder, remember, again, we're going to have to move it so that we are hitting, we make it into a parallelogram. So I'm going to take that, so I'm going to recreate a parallelogram. So I'm going to take this. You got to make it the same size as the other one. So obviously this would be easier with a ruler. Now I was lucky using the magic of the computer. I was able to redraw it using the clone function. For you, you would have to use a ruler and a protractor, but then you are going to solve. Okay. Start. Yeah, I'll try and do it through the computer later. Okay, now we're going to do this last one with the 6 newtons and the 23 newtons. Now they're both hitting at the same point, so again you would have to redraw this one. So redraw it and then draw the resultant. So we redrew it and then drew our resultant from start to finish. Now what I always tell you guys is if you have a vector going this way and a vector going down that way, the first thing I want you to do is figure out in your head which way it will go, because you're probably going to be right, because most of you would get that it would go somewhere in this direction. See how we're still going in the right direction? So you did it right. Alright, last thing I want you to work on is we have the 6 curve types. I told you you had to learn them. So we have the dt, bt, and at for constant velocity and a dt, bt, at for constant acceleration. I want you to try and draw them, and then I will tell you a little bit about them. So, put them into your notebook now. Alright, constant velocity. To have constant velocity, we have no acceleration. So, first thing we're going to do is draw no acceleration. So, it's right at 0. Then we're going to have, if we have constant velocity, that means velocity is not changing. So we would just have a line with velocity not changing. Now, last, if we have velocity staying the same, that means our distance is going to get bigger, but it's going to do it at a nice direct rate. So the slope of a dt graph is going to be velocity. So I draw little red arrows to help remind you the slope of velocity time graph is acceleration. I also put in the equation for slope, just in case there's one on the test. That would be y2 minus y1, x2 minus, oops, there should be x1. And then you would put, figure out units. If you put them in everything, it would be, in this case, meters over seconds. So now I want you to try the constant acceleration ones. So we have a dt, a vt, and an at. Well, for constant acceleration, my acceleration would stay constant, a straight line. So if my acceleration is constant, my velocity will keep going up, up, up. And the last one, the dt one. This is the one I keep telling you is hard to draw. So my guess is I'm going to have trouble drawing it using a mouse. But let's give it a whirl. Curve. There, nice parabolic curve. Now the area under our curve is going to mean something. The area under, like the velocity time graph, in this case is a triangle. So to remind you, it's half the base times the height. And then we just do the units. The base is measured in seconds. The height is measured in meters per second. Cross out the seconds, and I'd have meters left for distance. So the area of a velocity time graph would be distance. Alright, that is the review for today. You can work on block 1. Thanks, have a good day.